Marty. And first thing I'd like to do is to thank Peter and Sudeep for helping us with putting this talk together. Any faults remaining are mine, because if we listened to them, it would have been, of course, perfect. I'm going to talk about ATTRACTOR, which must be the best acronym in the world. My colleague Danette Allen and I are co-PIs on this project. We work, let's see if I can do this. Yes. We work with a large and talented team from 4 centers, Ames, Armstrong, Glenn, and Langley. And here is a subset of them. We also have participants from 4 universities, MIT, UIUC, Tufts, and CMU, with a very close collaboration. So what is our problem? We are looking at addressing the difficulty of flying in the new, at least perceived system with a very dense and diverse traffic of urban on-demand mobility and other environments. So to deal with this unprecedented complexity, we are, of course, asking for machine participation. We're asking for autonomous systems with authority. And the paradox is that to deal with complexity, we are involving autonomous systems, but the autonomous systems themselves introduce complexity in the form of uncertainty. So our overarching question is, how do we achieve trustworthiness and justifiable trust in autonomous cyber-physical human teams? And the critical point here is that our environment depends on safety. It is time-critical and certification-dependent. And of course, as Gary said, we can learn a lot about these problems from the surface traffic. However, 3D traffic is less forgiving than 2D traffic and therefore presents its own difficulties. So first, to set the stage, what do we mean by trustworthiness and justifiable trust? Traditionally, historically, trustworthiness was equated with reliability of the systems. However, as soon as we have systems that are controlled by software, we need to dig a little deeper. So trustworthiness is the attribute of the cyber-physical human system itself. What it is the assurance that the system does what's needed and doesn't do what it should not do. And it's a prerequisite to deploying the system in a safety-critical environment. And here's the other side of the coin. Trust is the property of the users of the system, and actually all participants in the system. And it's acceptance of decisions and directions from other agents. So we separate these. However, there is a feedback loop between the two. Trustworthiness of the system depends critically on trust, because the system, if the system is trustworthy but we don't trust it, that reduces the reliability of the system itself. So these are the definitions, and these are the issues we are trying to deal with. So, of course, we know about some famous/infamous breakdowns in trust and trustworthiness, and I'll give you some examples as a means of introducing what we're trying to do in ATTRACTOR. So, the Air France accident. Of course, that was a perfect storm of all the problems that can happen in human-machine interactions and in the trustworthiness of the vehicle itself. It's a big system question. So what we're trying to do in ATTRACTOR is to have a representation of all the possible trustworthiness and uncertainties issues in the system, rather than looking individually at factors, at separate factors. Of course, the miracle of the Hudson accident, we all know the geese did it. However, what's not frequently mentioned is this 30 seconds where the second pilot was trying to restart the engines, and the machine intelligence would not let him do that. So there is the question of the authority. Who has the final authority? And this is one other critical question that we're trying to answer in ATTRACTOR. And finally, everyone, of course, is familiar with the Boeing incidents of the past year and a half or so. And the big question here is the size and the boundaries of the system. Whenever we design the system, we define its boundaries. And so certification, human decision-making on how to certify, when to certify, who has responsibility, is actually part of the system design. So in ATTRACTOR, we are trying to specify what it means to have an appropriate boundary for the system. So trustworthiness of what? Because we're talking about control, it's a trustworthiness really of our decision making, because every step moving from point A to point B, making any action, it depends on the decision. It's really a decision making problem, an algorithm or a process, and it doesn't matter whether it's a human or a machine who does it. Of course, what matters is what properties are injected into decision making based on whether it's a machine or a human. So when is a decision worthy of trust? Let me show you an ideal case here, and I hope this works. So here is our ideal case. We have a very dense airspace here, but everyone shares the rules and everyone knows each other's rules. And it does not work. How do I run this without actually clicking on the slide? All right, someone is clicking. Thank you very much, invisible person clicking on the slide. So here we have just a few rules, but everybody shares those rules. And we had about 5,000 aircraft in the air, and nobody died. Now, thank you, there it is again. And take my word for it, none of these particles died. But what is trustworthiness really? Here we have a single participant in the system. It needs to move from point A to point B. What does it have to do? It has to make a decision. What we're doing in ATTRACTOR is formalizing the decision, coming up with a representation of the decision so they can be manipulated and evaluated. And forgive the math here, but I had to put some math. I'm a mathematician. So this is really formally an optimization problem given uncertainty. It's an uncertainty-based optimization problem. And if we have uncertainties in each component, from sensors to decision-making to perception, we can propagate the uncertainties all the way to the solution. So, as I mentioned, lots of uncertainties, and at the end, we can give you the uncertainty in the solution itself. Now, let's increase the size of the system. Each of these objects in the system has their own model of uncertainty, has their own model of their behavior. And they also need to not just evaluate their own state, they need to know about the mental model of the other participants in the system. So that tells you about how complicated the overall uncertainty estimation is. Why are we interested in estimating uncertainty? It's because trustworthiness is the inverse of risk. And so in order to give you a measure of trustworthiness and to be able to design for a trustworthy system actively, we have to be able to measure trustworthiness and trust in the system. So here is the big statement. Building trust and trustworthiness that is amenable to certification has to do with context. It has to do with formal maximizing of justifiable trust, and it has to do with thresholds. So let's not kid ourselves. There is going to be a subjective element in the system, and the subjective element has to do with everyone agreeing on when it is appropriate to take a certain risk. But once you agree on the thresholds, everything else can be formalized, the context and maximization of justifiable trust. So, of course, what we want to do in the uncertainty quantification, the uncertainty bounds need to be pretty good. We can't have such a huge uncertainty that the system becomes unusable. So a lot of the work that we're doing is in understanding the uncertainty and providing tight bounds on the uncertainties. But we need context in order to develop something tangible in the system. And our context is a search and rescue mission. It's a mission that is very widely applicable to pretty much moving from point A to point B and also to other areas. So in the mission, we are defining what needs to be searched. That's done with human or machine. The pre-mission modifications are designed through human-machine interactions, through natural human-machine interaction, which we claim facilitates trust. Throughout the mission, we run risk-aware planning in estimating uncertainties in the mission at each stage. We have reliable, analyzable trajectories that are generated. And finally, the mission can be simulated before it is flown. It can be approved. And finally, there is the execution of the mission that is done in a risk-aware fashion, and the risk is connected with vehicles, terrain, people, weather, and so on. And of course, the loop repeats at the number of steps that are predetermined or dynamically determined. So here is the system on which we're developing our components. And one of the crucial components here is to have a persistent modeling and simulation, mixed reality modeling and simulation. And so we could liken it to the digital twin for mechanical artifacts, but what this is for the ecosystem is a system that ingests data in real time and can model decisions and suggest decisions to the system. So here is our current state. We have a researcher who is potentially lost. The researcher is headed to a building but hasn't been detected there. So we are unleashing a fixed-wing aircraft to look for the researcher. And at the time, of course, we are practicing the trustworthiness, trust, uncertainty components in the system. So it turns out that the fixed wing cannot locate the researcher under the tree canopy and is asking for another asset. There was a decision making at that point. So a drone is now looking for a researcher in a cluttered environment, also making decisions based on the risk and uncertainties, and finally determines that it too cannot go beyond the clutter of the trees. And so here you observe the mix of the actual physical performance and simulation performance. So now a set of small surface drones is beginning to look for the researcher. The mission is being simulated before it is being run. And finally, we are using machine learning-based human detection to identify our wandering genius. So, found. Happy ending. So the reason I was showing you this is to give you this sense of our platform. But within every decision making, what we are practicing is the uncertainty estimation and risk evaluation for decision making. And so finally, to conclude, all this work that we're doing is really completely cross-cutting for decision making under uncertainty. What we're trying to do, of course, is to build measurable, the emphasis is on measurable, sense of trust and trustworthiness, where we can actively design for maximally trustworthy systems. Now, something I hadn't mentioned, but what's important here is that if you have a huge sense of uncertainty about the system, huge measure of uncertainty, what this really means is that you might have to restructure your system. So the risk gives you criteria for redesigning your system, increasing control in the system, increasing order in the system. So this is applicable both to system design and to system operations. I'd like to point out that the problem, to the best of our knowledge, has not been yet solved and not even realized that the problem is there. So last word about transition. This last year, we were lucky to win a humanitarian award at the AUVSI Exponential meeting, and we've met several companies there, actually not companies, but actually first responders from various agencies, state and city, and they're very interested in the tech transfer for at least our SAR product. So on the one hand, we are doing the fundamental trustworthiness work, and as a nice side effect, we have this SAR product that we are hoping to transition to assist in finding other lost people. So thank you very much for listening.
Well, I will quickly introduce one of the new additions here. Jim, would you like to say a few sentences about yourself? Yeah.
Can you hear me?
Yeah, you can sit down. That's fine.
Great. Yeah, first off, thank you very much for having me out here. My name is Jim Lockheed. I'm with JetBlue Technology Ventures. We are a travel industry and aerospace industry early stage investor. Personally, I've been in the aerospace industry for quite a while, starting with actually being an avionics technician in the Air Force and then flying surveillance drones for Boeing for a number of years around the world and managing operations for them before doing some startup activities of my own in the drone space. So again, thank you very much.
Thank you for joining us. And we have Viren and Peter, now time-tested VCs already. So Natalia, thank you for attractive presentation. Let's start. Who wants to go first? Peter, you want to start with commentary, or you? Viren? Okay.
Go ahead. I mean,
Oh, we'll start with left.
sure.
Yeah.
So I have a question around the shared certification level and how we're going to deal with sense and avoid. Are you seeing that there's going to need to be one single basis for your sense and avoid response that all, let's say, UTM or just unmanned vehicle manufacturers would need to actually share for this solution to work?
So that would be very nice. I don't know if I'm Yes, that would be very nice. I don't know if it's realistic. There is, of course, the question of availability. You can buy a drone at any 7-Eleven, so I don't really know that it's possible to require that. Where I think it would be great to have is at certain areas of operation. So if there is a way to limit access to some areas of operation based on the technology and shared rules one has, then I think that might be a necessity, but I'm not sure if it's actually an enforceable condition.
Okay, so it'd probably be more for specific use cases or specific organizations.
I would imagine so.
Yes. Okay, thanks.
Yeah, and this is more a question of understanding on my part. So, did I understand it right that before you go into a rescue mission, you actually simulate, first of all, and before you embark on that mission? Is that partly what your system does?
You can, and not just before you go, but at any stage you can run a simulation,
Okay.
given the latest data that you have.
Okay, okay. So it's as much to assess, I guess, how risky the system is, and then adapt the system as much as to sort of plan and navigate some upcoming operation, if you will, right?
Exactly,
Okay.
exactly. Especially, say, if you're looking for someone in a really safety critical environment, such as a building after an earthquake, a collapsed building, you probably want to do a serious assessment. So just to clarify, there are two ways to use this risk assessment. One is a priori, before the overall system design altogether. And then there is one at each stage. So if your altogether risk assessment is too large, that may indicate that you need to change fundamentally how you approach the mission. So to give you an example, if there is no one up in the air, you can go take your greatest circle route wherever you want. But if everyone is going to a football game, then you probably want to have a much more structured traffic there.
Right.
Just an example.
And have you actually deployed or somebody utilized this system in a real situation, or how close are you to doing that?
So parts of it are very close. So first of all, no, we have not
Okay.
found anyone yet. Second of all, it is reasonably ready to deploy for a limited set of targets. So for instance, we have a human finder. But we have not, at this point, injected all the risk work into the physical system yet.
Okay. Any sort of, I don't know, can you guesstimate how complete you are? Is it
It's
20,
a
50?
very hard question to answer. The problem is that there is a lot of unknowns. There are a lot of unknowns. So if you take a single vehicle, there are sensors unknowns, battery unknowns about just the state of the vehicle itself. And some of that information is not even readily available, so you have to take guesses. On the mathematical side, we're all parametrized, so we can kind of give you a generic answer, but it's the tightness of the bounds that is important for the practical application. And for that, it may take quite a while. I'm thinking if we do the complete risk assessment, that's another maybe a year and a half or so. Without particularly risky areas, say looking for someone in the forest, I'd say within a year that would be somewhat attainable.
Okay, thank you.
So in the work that you've done so far, can you talk about what that has uncovered for you in terms of the types of metadata that you would want to see coming off of the whole system to describe the quality of the inputs and the feeds that you have coming in order to create these measures of trustworthiness?
Yes, so there are several big gaps which need to be filled in. And some of them are not really up to us. So manufacturers of sensors, manufacturers of batteries, they need to really give us the data on what is it. If you're seeing something, what's your plus minus? How long does the battery operate until it fails? And these are hard to come by, if not impossible to come by, because it's something that industry needs to share, and that may be, actually it was outlined as one of the big questions during a recent ARMD workshop on autonomy, that this kind of data is needed about the health of the overall health of the vehicle. The second big thing, and that is a theoretical unsolved problem, what is the trustworthiness of visual perception of an object? So right now, visual perception relies on machine learning. In some instances, of course, there are other ways to judge distance from objects, but if you're recognizing objects, that's a machine learning based area. And there is no fundamental bound on the accuracy of that. Moreover, it's fragile. It will work great until it fails, and there is no similar component to, say, trustworthiness of control. In control, you know the safe envelope. In machine learning, you don't know the safe envelope. So these are still big gaps that need to be breached in terms of data.
So for the sensors, is it vision only, or do you use other?
We
Sensing
use others. So, for instance, in the work that we're doing with MIT, we're looking at GPS-denied environments, for instance, and they use LiDAR.
Yeah, I was
They
thinking,
use inertial units, but ultimately to recognize something visually, you do need visual recognition.
I mean, so similar, I would think, if you're not already, I would think using a combination of LiDAR, radar,
It
vision,
is.
the usual
Yes.
autonomous
We are.
stuff makes
Mhm.
sense here. Yeah.
But the final thing, if you want to detect the foot of somebody sticking out of
Yeah.
the bushes,
Yeah, absolutely.
you gotta
Yeah,
have
yeah.
visual.
Marty, how much time do we have?
5 minutes.
Okay. Anybody else? Jim, what do you want to?
So I see this being, sorry.
can also take
Yeah, really quick. So I see this being as a risk assessment and a planning tool primarily, going to simulate your mission basically to consider what variables you might run into. How much of this would be done ad hoc, or if things change, could this system adapt, create a new plan, or affect the mission? Or is it all
Absolutely.
pre-planning
So
right now?
it is meant equally as mission planning and mission design tool as a real-time operational tool. Both.
Okay.
Absolutely.
And would that take that human-machine interaction at that point, probably?
Indeed. So something that I haven't shown in terms of building trust. How much do we have for minutes? Can I show one extra slide, or are we already off the
No,
slides?
can we go back to the slides, Ricky? You have it in the backup?
Yes, I have it in the backup. That might actually
Sure.
help with that question.
But in the meantime, you can keep talking.
Yes. All right. All right. I could actually do both, chew gum and walk. All right. So the idea
But
is
that
this.
trustworthy?
We need. Not if I'm in high heels now. So here is where we are in terms of human trust, machine building, human machine building trust, what we might want to have. So suppose here we are in a mission. This is in real time. And could someone start, please, the invisible helper? Thank you. So here is a mission. The machine is doing its autonomous thing. And then it gets to an area where the human wanted it to go, but it doesn't want to go there. So the machine on its own modifies the trajectory, and the human is arguing. So there is a pull between them. The machine agent resists the modification. And so the type of interaction we might have, which would go into developing trust, but it's a real-time interaction, is this. The machine says, I want to change. The human says, why? The machine says, because kids came out of the kindergarten. Are you sure? Here is the proof, the image of children. What's your new trajectory? Here is the trajectory, but there are several. Which one am I proposing? And so presumably the machine would propose the one with the lower risk, but there is a very well-known problem in how humans make risk-based decisions. So how do you present uncertainty to the humans so they do make the right decision? So this is an example of a real-time interaction and risk assessment.
Go back to the IO. Can we go back to the IO chart? Or display? We got a couple minutes.
Yeah. All right. Let's see, we already know the second question, but do you see appropriate focus on reducing uncertainty or building solutions?
I'm sorry, do I
The first question.
It's not an either or. Reducing uncertainty means building a solution, in my opinion. Uncertainty reduction is a necessity so you can generate a solution within practical bounds that can be followed safely.
So let me ask you this question. How much of this really needs to be machine learning and how much of this could be deterministic or pretty well coded, time-tested, verified, validated?
So I think machine learning right now, the only place where machine learning has to be, because we don't have other ways of dealing with that, is the image recognition. Everything else, if we have sufficient control, can be done without machine learning. but I don't know right now of any other way of recognizing. Of course, you can do without if you change your infrastructure in a way that reduces the need for recognition. Say, if you restrict autonomous cars to moving in a tunnel where there is not going to be a pedestrian jumping in front of them, then you don't need to recognize the pedestrian. So that's the big question about the safety of the system and the needs and the technology. But identifying these uncertainties, I think, is crucial, because some of them are irreducible, but some of them are reducible.
Yeah. All right.
Thank you.
Thank you.